I want to start today with a bit of a thought experiment.
Right.
Imagine you wake up, you walk into your kitchen and you turn on the tap and, clear, safe water comes out.
Right. The usual.
The usual. You flip a switch, the room floods with light, you open the fridge, you grab a yogurt, maybe some strawberries. It's just a completely mundane Tuesday morning. But if you actually stop for a second, and I mean really stop, and peel back the layers of reality that make that Tuesday morning possible, you realize you're standing in the middle of this massive invisible machine.
It's the ultimate invisible infrastructure, isn't it? We navigate our lives assuming these things, water, power, food, are just there.
Yeah, like air.
Exactly like air. But they aren't natural occurrences anymore. Not in the way we use them. They are engineered.
Precisely. And that's what we're doing today. We're looking at this whole stack of research on the scientific frameworks that power our civilization.
And this isn't a textbook reading.
No, definitely not. We're looking at how we've effectively hacked the planet, really, using three main tools: physics, chemistry, and biology.
Which is a great way to frame it. Because we usually learn these subjects in silos, right?
Totally separate.
You go to physics class to learn about forces and energy, then you go to biology to learn about cells. But in the real world, in the systems we rely on every single day, they're completely entangled.
You can't separate them.
You just can't. You cannot have modern agriculture without chemistry. You cannot have an energy grid without physics. It's all connected.
And we have a huge stack of sources for this deep dive. I mean, we're going to cover everything from, and I love this, ice stupas in the Himalayas.
Incredible story.
To robot farmers and even purple tomatoes that might, fight cancer. But before we get into all the gadgets and the cool breakthroughs, I think we have to touch on the operating system running all of this.
The scientific method.
The scientific method, which I think is often misunderstood as just a classroom exercise.
Oh, absolutely. People remember it as a 5-step checklist.
Right. I feel like most people remember it as make a guess, do a test, write a report, get a grade. But looking at these sources, it strikes me as something much more, aggressive than that.
That's a good word for it.
It's a mechanism for error correction. It's designed to prove things wrong.
That is the crucial distinction. Science isn't just about accumulating facts and being right all the time. It's a cycle. Observation, hypothesis, experiment, analysis. And that cycle is designed to be ruthless.
Yeah.
It's the only tool we have that lets us separate what we hope is true from what is actually true.
And every single piece of technology we're going to discuss today, whether it's a nuclear reactor or a hydroponic lettuce farm, exists because someone, somewhere, observed a problem, hypothesized the solution, and then just rigorously tested it until it worked.
Or until it failed, and they learned from the failure and tried again.
Exactly. And that journey, that transition from a guess to technology, that's what we're tracking. So let's dive in. Let's unpack that first pillar. Food, and specifically the future of farming. Because that old image of the guy in overalls chewing on a stalk of wheat, that's rapidly becoming a vintage aesthetic.
It is. The reality is looking a lot more like a laboratory. We're seeing this major shift toward what you could call high-tech, low-impact agriculture.
And one of the most significant developments here seems to be hydroponics.
Soilless farming.
Okay, so let's get into the mechanics of this. Hydroponics means growing plants without soil. My immediate thought is, if you take away the soil, you're taking away the plant's home. It's like, how do you support the biology without the geology?
You have to strip the process down to its absolute most basic needs. What does a plant actually need from soil?
Water, nutrients.
Right. It needs physical support for its roots, it needs water, and it needs dissolved mineral nutrients. That's really it. Soil is just the container for those things.
It's the delivery system.
It's the delivery system. So if you can provide that physical support with a sterile medium, something like coconut coir or rock wool, which is basically spun volcanic rock.
Like insulation.
Kind of, yeah. And then you deliver the nutrients directly to the roots through a water solution, well, the soil becomes redundant. You don't need it.
And the efficiency stats here are, they're just wild. The research mentions that hydroponics uses up to 90% less water than traditional farming.
Right.
And that just feels backwards to me.
Yeah.
You're growing them literally in water, but you're using less of it. How does that math work?
It does seem counterintuitive. I get it. But it all comes down to waste. or the lack of it. Think about a traditional field.
Right.
You spray gallons and gallons of water over acres of land. A huge percentage of that evaporates immediately into the air before it even hits the ground.
Especially in a hot climate.
Exactly.
Huh.
Or it drains down past the roots, deep into the groundwater where the plant can't reach it. It's incredibly wasteful when you think about it.
Whereas a hydroponic system is a closed loop.
Precisely. It's a recirculating system. The water with the nutrients flows past the roots. The plant takes exactly what it needs and the rest. It goes right back into the reservoir to be cycled around again.
So virtually nothing is lost.
Almost nothing. No evaporation to speak of, no runoff polluting nearby streams. It's a surgical application of resources.
There was a visual in the source material that I found absolutely mesmerizing. It's a facility in Rikuzen, Japan, and it doesn't look like a farm at all. It looks like some kind of sci-fi centrifuge.
Oh, that's a circular hydroponic setup. It's brilliant. It's a design that solves a few specific problems at once. Lighting and space, mainly.
So how does it work? It's like a giant spinning record of lettuce.
Pretty much. In this design, the lettuce is planted in a continuous spiral on a big circular bed.
And it rotates.
Right, yes, very slowly. The seedlings start in the center of the circle, where they're tiny. The entire bed rotates, and as the days pass and the plants grow, the spiral mechanism pushes them further and further out toward the perimeter.
So it's like a time lapse, but in physical space. The youngest, smallest plants are in the middle, and the big, ready-to-harvest ones are on the outside.
Exactly. And by the time they reach that outer edge, which takes roughly 30 days, they're full-grown heads of lettuce ready for harvest.
That's just so efficient.
It maximizes the light exposure for every single stage of growth, and it completely automates the movement of the crop. It's a factory line, but for biology.
Now, if we want to make this system even more complex, and I would argue more elegant, we can add another biological player to the mix.
Yes.
Aquaponics. This is where we introduce fish.
Aquaponics is this beautiful combination of aquaculture, which is just fish farming, and hydroponics. And this addresses one of the main inputs of a hydroponic system, fertilizer.
Okay, so in a normal hydroponic setup, you're buying bottles of chemical nutrients and mixing them into the water.
Right. You have to provide the nitrogen, the phosphorus, all of it. In aquaponics, the fish provide it for free.
This is the part that always fascinates me because it turns a waste product into a critical resource. Fish produce ammonia.
They do. Fish excrete waste, mainly through the gills. And that waste breaks down into ammonia. Now, in a regular fish tank or an aquaculture farm, ammonia is highly toxic.
And it'll kill them.
It will. If the levels get too high, it literally burns their gills and they can't breathe. So you have to constantly filter it out or do massive water changes.
But in this system, you take that dirty, toxic water,
and you pump it into the plant grow bed.
which seems like a terrible idea.
It would be, except for the invisible microbial heroes that live in the grow bed media. There are bacteria that colonize the system. One type of bacteria converts that toxic ammonia first into nitrites, which are still toxic.
Still bad.
But then a second type of bacteria comes along and converts those nitrites into nitrates,
Then nitrate?
our perfect plant food. Plants love nitrates. They suck them up as fertilizer, and in doing so, they scrub the water completely clean.
So the clean water then flows back to the fish tank.
And the whole cycle starts again. It creates this perfect symbiotic loop. The fish feed the plants, and the plants clean the home for the fish. It's a mimic of a natural ecosystem, but optimized for food production in a tiny footprint.
It's literally engineering nature to do what it does best, just in a much smaller box. But, we have to be realistic here. Most of the world's calories still come from the ground.
Oh, absolutely.
We aren't growing wheat and corn and soybeans in aquaponic tanks just yet, so we have to talk about soil science.
And soil is so much more complex than people think. It's not just dirt. It's a living matrix. It's minerals, organic matter, water, air, and a universe of chemistry.
And one of the most critical factors that farmers have to manage is something we all learned about in high school chemistry, pH.
The pH scale, yeah. I remember it well.
0 to 14, 7 is neutral.
Correct. 0 is highly acidic, like battery acid. 14 is highly alkaline, like bleach. 7 is pure water. And most plants, they have a very narrow window where they're happy.
Right in the middle, around 6 or 7.
That's their sweet spot.
And the thing that stuck out to me in the reading is why this matters so much. It's not that the acid, dissolves the plant roots or something that dramatic. It's about nutrient lockout.
That is the key concept. You can have soil that is incredibly rich in all the things a plant needs. Iron, magnesium, nitrogen, you name it. But if that soil is too acidic, or too alkaline for that matter, Chemical reactions occur that bind those nutrients to the soil particles.
Because they're stuck.
They become insoluble. The plant roots can be sitting in a buffet of nutrients but literally starve to death because they can't physically absorb them. The door's locked.
So the farmer's job is basically to be a chemist. They have to constantly monitor this and adjust it. If the soil is too acidic, which I gather happens a lot with rain and decomposition, what do?
They look to geology, actually. The standard solution for acidic soil is agricultural lime.
Which is just limestone.
Yeah. Crushed limestone, yeah. Calcium carbonate, it's alkaline. So you spread this rock dust over the field, it dissolves into the soil, and it reacts with the acid, neutralizing it. It brings the pH back up into that sweet spot where all the nutrients unlock again.
It's like a key for the pantry.
A perfect analogy. And it also encourages earthworms and beneficial microbes, which improves the soil structure. It's a fundamental tool.
There is a beautiful example of this chemistry in the wild that I think makes it really tangible for everyone.
The hydrangeas.
The hydrangeas.
The hydrangea is fascinating because it basically behaves like a natural litmus test. You know those little paper strips you used in school?
Right. So if you're walking through a garden and you see a bright blue hydrangea, what does that tell you about the ground it's in?
It tells you the soil is acidic. In acidic soil, a mineral, aluminum, becomes available to the plant. The plant's roots absorb that aluminum, and the plant incorporates it directly into its pigment, which turns the flowers blue.
And if the soil is alkaline?
The aluminum is locked up. The plant can't get it, no matter how much is in the soil. So the flowers bloom pink or red.
So you could literally walk through a neighborhood and map the soil chemistry just by looking at the color of the flowers in people's gardens.
You absolutely could. It's chemistry made visible.
That is a perfect transition, actually, to our next section. We've talked about the chemistry of the soil, but now I want to zoom in on the chemistry of the food itself. We're calling this section the microscopic chef.
This is where biology really meets chemistry, right in the kitchen.
We tend to think of bacteria and fungi as the bad guys, you know? If there's mold on my bread, I throw it out. If my milk smells funky, it's going down the sink. But the research points out that some of our most culturally significant foods are basically controlled rot.
Controlled spoilage is a very accurate term for fermentation. It's a metabolic process. What you're doing is inviting very specific microbes, certain bacteria or yeasts, to a feast.
A feast on your food.
A feast on the sugars in your food. And as they consume those sugars, they produce byproducts. And those byproducts are what transform the food.
Okay, let's look at cheese. Because I love cheese, but when you describe the process mechanistically, it sounds, well, kind of horrifying.
It is a profound biological transformation. To make cheese, you start with milk and you introduce specific strains of bacteria. Their job is to consume the lactose, that's the sugar in milk, and convert it into lactic acid.
And the acid is what changes the structure of the milk proteins.
Exactly. It creates an acidic environment where the casein proteins, the main proteins in milk, denature and clump together. That's curdling. The milk solidifies into curds, separating from the liquid whey.
But the microbes aren't done yet, are they? Especially with aged cheeses.
Oh, not at all. In things like an aged cheddar or a Parmesan, you have these aging cellars, where specific molds and bacteria continue to work on that cheese for months or even years.
What are they doing in there?
They're breaking down the fats and proteins into new, more complex flavor compounds. That sharp, nutty, complex flavor of an aged cheddar or that pungent kick of a Roquefort blue cheese. That is the direct result of microbial digestion.
So we're literally tasting the byproducts of millions of microscopic lives.
Delicious. Delicious byproducts. Humans have been making cheese for an estimated 7,500 years. It's an ancient biotechnology.
The one that really surprised me in the research, though, was chocolate. I had absolutely no idea fermentation was involved. I just thought you pick the bean, roast it, grind it up.
That's a very common misconception.
Yeah.
And if you did that, if you took a raw cacao bean straight out of the pod and roasted it, it wouldn't taste anything like chocolate.
What would it taste like?
Incredibly bitter, astringent. It would have none of that deep, rich chocolate flavor profile that we know.
So what's the missing step?
The beans, which are covered in this sweet, white, fruity pulp, are heaped into big piles, often right there in the jungle where they're harvested and covered with banana leaves. And they just sit there for 5 to 7 days.
So you just let it rot in a pile?
You do. The natural yeasts and bacteria in the environment are drawn to that sugary pulp, and they start a massive fermentation.
And it gets hot, right? The pile actually heats up.
Very hot. The chemical reactions generate a lot of heat, and the acids that are produced by the microbes penetrate the tough shell of the bean itself. This kills the germ inside. stopping it from sprouting. And it triggers a cascade of chemical changes inside the bean that create the precursors of chocolate flavor.
So without that messy, hot, smelly fermentation pile under the banana leaves, there is no chocolate bar.
There is no chocolate industry, period.
It's just amazing that humans figured this out. Hey, let's let this pile of beans rot for a week and then see if it tastes better.
Well, we've been doing it for thousands of years. Bread is the same thing. Yeast, eating sugar, and burping out carbon dioxide to make it rise. Beer, wine, kimchi, yogurt. These are all ancient biotechnologies. We just didn't know the word biotechnology back then.
But now we do know, and we've moved way beyond just using the microbes that happen to be floating around in the air. Now we are rewriting the source code.
Yeah.
We have to talk about genetically modified foods.
GM foods, a topic that is certainly controversial in the public sphere, but scientifically it represents a fundamental shift from selection to editing.
Right. Instead of breeding the best corn with the other best corn for 100 years and hoping for the best, you just go in and cut and paste the specific gene you want.
That's the essence of it, yes.
Yeah.
DNA is the instruction manual for building a living thing. Genes are specific pages in that manual that say things like, make the fruit red, or make the stalk tall and strong, or resist this particular disease. Genetic modification allows scientists to take a specific page from one manual and insert it into another to achieve a very precise desired trait.
Let's talk about a specific case study from the sources. The purple tomato. This sounds like a novelty item from a fancy grocery store, but the source says it's actually a potential medical tool.
This was developed by scientists at the John Innes Center in the UK. And they did something really clever. They took a gene from a snapdragon flower, specifically the gene responsible for producing that flower's deep purple pigment, and they spliced it into the DNA of a tomato.
And that pigment, that color, isn't just for show.
Not at all. The purple color comes from a class of chemical compounds called anthocyanins. These are powerful antioxidants, the same kind you find in superfoods like blueberries and blackberries.
And they have real health benefits.
Significant health benefits, yes. Studies have shown they can have anti-inflammatory properties and may even slow the growth of some types of cancer. By putting that gene into a tomato, which is a high-yield, widely eaten crop, you're creating a much more accessible vehicle for that powerful nutrient.
So it's biofortification. You're packing more nutritional punch into the same package?
Precisely. And then you have the defensive side of GM, which is maybe even more important. The story of the rainbow papaya is a perfect example.
This was in Hawaii, right?
Yes. In the 1990s, the papaya industry in Hawaii was on the brink of total collapse. It was being wiped out by the papaya ring spot virus. It was an existential threat to those farmers and their livelihood.
And traditional methods like breeding for resistance couldn't fix it.
Not fast enough. The virus was just too aggressive. So scientists developed a GM papaya. They engineered it to contain a small, harmless piece of a gene from the virus itself.
So it's kind of like a vaccine for the plant?
That is the perfect analogy. It inoculates the plant, allowing its own defense systems to recognize and fight off the virus.
And did it work?
It saved the entire industry. The rainbow papaya is pretty much the only reason we still have a thriving papaya industry in Hawaii today. It wasn't about making a bigger or sweeter fruit. It was about ensuring the fruit could exist at all.
It really is applying the debug phase of the scientific method directly to agriculture. But let's pivot for a second from pure biology to hardware. Because the other thing taking over the farm is the robot.
The robot revolution in agriculture it's happening, and it's happening fast. And it's really about tackling the labor problem. Farming is incredibly hard, repetitive, physical work.
And we aren't just talking about, remote control tractors. The sources are clear. We are talking about autonomous robots.
Correct. These are machines that are making their own decisions without direct human supervision using artificial intelligence and machine learning.
Okay, can we break down that term machine learning in this context? Because it gets thrown around a lot, and I think it can be a bit of a black box for people.
Sure. Think of it as training a dog. But the dog is a very powerful computer. You start by showing the computer thousands, maybe hundreds of thousands of images of a strawberry plant.
And you label them.
You label everything. This is a weed. This is a leaf.
Yeah.
This is a perfectly ripe strawberry. This is a green, unripe strawberry. This one has a bit of mold.
So that's the input, a massive amount of data.
A massive amount of data. The computer, the AI, then analyzes all those images to find patterns. What combination of pixels means red and ripe? What shape means spiky leaf of a weed? That's the analysis phase. Then when you put that robot out into a real field and its camera sees a new plant, It applies all those learned patterns to make a decision.
Spray the weed or pick the berry.
That's the output. Input, analysis, output. It's a learning loop.
The strawberry picking robot example is the one that really impressed me because strawberries are so delicate. You know, if I hand a robot a rock, it can grab it. But if I hand it a strawberry and its gripper squeezes just 1% too hard, I have jam.
That is the big engineering hurdle in agricultural robotics, the soft touch. Industrial robots, the ones you see in car factories, are designed for steel and plastic. They're about force and precision. A strawberry picker needs incredibly delicate sensors in its gripper to gauge pressure.
So it sees the ripe fruit, extends an arm.
And it has to pluck it from the stem without bruising the skin. It's a huge challenge.
And the speed is what makes it economically viable. The stat in the research is that one of these machines can pick up to 794 pounds of strawberries in a single day.
That is a volume that replaces a significant amount of human labor. And crucially, the robot can work in 247. It can work at night under its own lights. It can work in the rain. It completely changes the economics of the harvest.
And we're seeing this move off the farm, too. The sources mentioned Flippy, the burger bot.
Flippy is a great example of bringing that same sensor technology into the service industry, into a fast food kitchen.
What's its secret?
It uses thermal sensors and cameras. It monitors the exact temperature of the patty on the grill. It can see the color changing. It knows, based on thousands of data points, precisely when the chemical reactions of cooking, the Maillard reaction that makes it brown and tasty, are complete.
So it knows exactly when to flip the burger and when it's fully cooked.
To the second. It removes the variable of human error. No more undercooked burgers, no more burnt hockey pucks. Every single one is perfect. It's all about consistency for these high-volume, repetitive tasks.
Okay, so this is all incredible, but let's zoom out. We can have all the robots and purple tomatoes in the world, but none of it works without the most basic, most fundamental compound in chemistry, water.
H2O.
Yeah.
It is the ultimate limiting factor for civilization. We're entering an era of unprecedented water scarcity in many parts of the world. Yeah. And because of that, we are seeing major innovations in how we catch it, how we store it, and how we clean it.
The ice stupa project in the Himalayas is my absolute favorite story in this entire stack of research. It feels like something from a fantasy novel.
The Ice Wizards of Ladakh.
The Ice Wizards of Ladakh, exactly. Can you explain what this is?
So Ladakh is a region in the Indian Himalayas. It's a high-altitude desert. It gets very little rain. The communities there rely almost entirely on glacial melt for their water.
But the glaciers are shrinking.
They're shrinking fast due to climate change. So what's happening is in the spring, when farmers need to plant their crops, the streams are dry. The water from the high-altitude glaciers doesn't start flowing down until late summer, which is too late for the growing season.
So they have a timing problem. They have water, but at the wrong time of year.
A critical timing problem.
Yeah.
So they decided to store the winter water. In the winter, streams are flowing with meltwater, but nobody needs it for farming. So they run a simple pipe from a stream high up the mountain down to the village.
And then?
They point the pipe straight up in the air. The water shoots up like a fountain, and because the winter air is well below freezing, it freezes instantly as it falls. Over the weeks, it builds up this massive, towering cone of ice. The stupa.
And I have to ask about the shape. Why a cone? I know stupa is a reference to a Buddhist religious structure, so is it a cultural thing?
The name is cultural, but the shape is pure geometry and physics. Think about an ice cube on a hot sidewalk versus a snowball.
The ice cube melts way faster.
Way faster. Why? Because the flat cube has a huge surface area exposed to the sun. A sphere or a cone has the minimum possible surface area relative to the volume of ice inside.
So the cone shades itself. The sun only hits one side at a time.
It does. By building these massive cones, some are over 70 feet tall and can hold 500,000 gallons of water, they create an artificial glacier that melts very, very slowly. It lasts all the way through the spring sun, releasing a steady trickle of water right when the farmers need to irrigate their fields.
It's storing time. It's literally storing winter to use in the spring.
And the best part, it costs almost nothing to run. It's all powered by gravity and the cold air. It's brilliant.
Then you have the places that don't freeze, but they have fog. The fog catchers.
This is another low-tech, high-impact solution. It's used in places like the Atacama Desert in Chile or on Mount Boutmezguida in Morocco. These are incredibly arid environments. They get these thick, dense fogs rolling in from the ocean.
So fog is just water vapor. It's a cloud on the ground.
It's a cloud on the ground that hasn't rained down yet. So the challenge is, how do you catch a cloud?
How do you catch a cloud?
You use a special kind of mesh net. It looks a bit like a giant volleyball net, but with a very specific weave. Now, you can't use a solid sheet of plastic because the wind would just blow right around it, carrying the fog with it.
Aerodynamics. You need the wind to pass through.
Right. As the foggy air passes through the thousands of fibers in the mesh, the tiny water droplets collide with the fibers. They stick. Then they merge with other droplets. They get heavier and heavier, and eventually gravity pulls them down into a collection trough at the bottom.
It's basically combing water out of the air.
A perfect description. And the cloud fisher system that's mentioned in the notes, a specific design, can collect up to 130 gallons of fresh water a day from a single net.
That's life-changing for a remote village.
It's transformative. It means children, usually girls who used to spend their entire day walking miles to a dirty well, can now go to school instead. Simple physics having a massive social impact.
Okay, now, for the one that went viral a few years ago, the shade balls.
Yeah.
The Los Angeles reservoir covered in millions and millions of black plastic balls. It looked like a giant ball pit from a fast food play place.
People laughed at it, they made fun of it, but the science is incredibly sound. In a place like Southern California, in a drought, evaporation is your mortal enemy. By floating these balls on the surface of the reservoir, you block the sunlight.
And that stops the water from turning into vapor.
It reduces evaporation by 85 to 90%. We're talking millions of gallons of water saved every year just by covering the surface.
But there was another reason for the balls, right? The sources mention a chemical reason that's less obvious.
Yes, and this is a great example of unintended chemical consequences in a water system. The reservoir water contained naturally occurring bromide. It also contained chlorine, which we add to the water to sanitize it.
Standard practice.
Standard practice. But when you mix bromide, chlorine, and sunlight, specifically UV radiation, you get a chemical reaction that creates a nasty compound called bromate.
And bromide is bad.
It's a suspected carcinogen. The city was having trouble keeping the levels below the legal limit. So the balls weren't just stopping evaporation, they were acting like a giant pair of sunglasses for the reservoir. They blocked the UV radiation to stop that specific chemical reaction from happening.
So clever. It solves two problems with one very strange-looking solution. We're literally engineering the environment of the reservoir.
We are.
And finally, on water, we have to talk about the water we throw away. Wastewater.
Which we treat as garbage, but it's actually a resource full of valuable materials.
The process of cleaning it is, again, basically speeding up what nature does. I was reading about the first step, sedimentation.
That's just gravity at work. You let the wastewater sit still in a huge, quiet tank. And what happens? The heavy stuff, the organic solid waste, sinks to the bottom.
And the light stuff?
The light stuff, grease, oil, scum, floats to the top. So you just scrape the top and you pump out the bottom. It's a simple physical separation.
And that stuff at the bottom is called sludge, which I have to say is not an appealing name.
It's not a great marketing term, no. The industry prefers biosolids. And once this sludge is collected, de-watered into what they call a sludge cake, and treated to remove any harmful pathogens.
It's useful.
It's incredibly useful. It's rich in nitrogen and phosphorus, the two key components of fertilizer.
So we put it back on the farm.
Exactly. We use it as fertilizer. It closes the loop. The nutrients from the food we ate that we flush down the toilet go back into the soil to grow more food. If we just dump it all in the ocean, we're breaking that nutrient cycle and slowly but surely depleting our farmland.
Okay, so we've covered food and water, two pillars of survival. Now we need to power all these pumps and robots and lights. Let's talk about energy.
This is the realm of pure physics, energy generation and transmission.
I want to start with the thing we all use, but I don't think many people understand, the grid. How does electricity actually get from a power plant to my house to toast my bread? It's not like water in a pipe, exactly.
It's a surprisingly good analogy, though. Think of voltage as the pressure in the pipe. If you want to push water through a really, really long hose, you need very high pressure.
Right, or it just dribbles out the end.
Exactly. It's the same with electrons in a wire. If you want to push them over hundreds of miles from a power plant to a city, you need incredibly high voltage.
And if you don't use high voltage, what happens?
You lose most of the energy as heat.
Mm-hmm.
The natural resistance of the wire just eats it up. It bleeds away. So when electricity leaves a power plant, the first thing it does is go through a step-up transformer. This boosts the voltage massively, up to 400,000 volts, sometimes even more, for the long-distance journey on those big steel transmission towers.
But if 400,000 volts came into my house, my toaster would. Well, it wouldn't exist anymore.
Your whole house would explode.
Yeah.
So when the power line gets to your neighborhood, it goes through a step-down transformer. Those are the gray cylindrical boxes you see on utility poles. That lowers the pressure, the voltage, back down to a safe and usable 110 or 220 volts.
So the whole grid is this constant management of pressure, balancing the efficiency of long-distance travel with the safety of home use.
And that grid is becoming infinitely more complex now because the source of the power is changing. We're moving away from centralized plants and toward distributed generation, like solar.
The source material had a stat that just blew my mind. 1 hour of sunlight hitting the surface of the Earth contains enough energy to power the entire planet for a full year.
The energy is there. It's bathing us in it every day. The challenge is catching it efficiently.
So how do solar panels, photovoltaics, actually work?
It's a quantum effect, really. You use materials like silicon that are semiconductors. When photons, particles of light from the sun, strike the silicon atoms, they have just enough energy to knock an electron loose. And a flow of electrons is, by definition, an electric current.
And we're seeing this scale up in incredible ways. The research mentioned the MS Turnor Planet Solar Boat.
An amazing machine. It's covered in over 5,000 square feet of solar panels.
And it went around the world.
It circumnavigated the entire globe without using a single drop of fuel. It proves that solar isn't just for pocket calculators anymore. It can move heavy tonnage across oceans. We see it on the International Space Station, powering an entire habitat.
But the sun sets. The wind stops blowing. And that brings us to what might be the single biggest bottleneck in modern physics.
The battery problem.
Storage.
It's all about storage. We have incredible generation capacity when the sun is shining or the wind is blowing, but we need that power at 8 p.m. when everyone gets home and turns on their TV and their air conditioning.
And when we say batteries, we're not just talking about the AA things in my TV remote.
No. We need grid-scale storage, massive systems. And we're looking at all kinds of ways to store that potential energy. There's chemical storage, like giant lithium-ion battery banks, basically scaled-up versions of your phone battery.
Okay.
There's kinetic storage, huge, heavy flywheels spinning in the near-perfect vacuum, holding energy in their momentum. And my personal favorite, gravitational storage.
This is the pumped hydro system, right?
Yes. It's beautifully simple. You find a location with 2 lakes or build 2 reservoirs, one at the bottom of a hill and one at the top. When you have extra solar power at noon, you use it to power a pump that moves water from the bottom lake up to the top lake.
You're literally pushing weight uphill against gravity.
You are turning electrical energy into gravitational potential energy. The water just sits up there, holding that energy. Then at night, when you need power, you just open a valve. The water rushes back down the hill through a pipe, spins a turbine, and generates electricity on demand. The battery is just a lake full of water sitting on a hill.
It's so elegant, so simple. But we have to address the heavyweight champion of energy density. We have to talk about nuclear.
Nuclear fission. On a pure energy per pound basis, nothing else comes close. A single pellet of uranium fuel, about the size of a gummy bear, contains as much energy as a ton of coal.
And the mechanism is splitting the atom.
That's it. You take an unstable atom, like uranium-235, and you fire a neutron at it. The nucleus absorbs the neutron, becomes incredibly unstable, and splits apart. This releases an immense amount of heat, and it also shoots out more neutrons,
Which then hit other atoms.
which hit other uranium atoms, causing them to split. That is the chain reaction. You control that reaction with control rods to keep it stable.
And all that incredible heat, what does it do?
It boils water.
That's it.
That's it. All that high-tech, mind-bending nuclear physics is just the world's most complicated and powerful way to boil water. The resulting steam turns a turbine, which spins a generator, just like in a coal plant or a natural gas plant.
Okay, I have to ask about the cooling towers. We all have the image from the Simpsons intro, the big hourglass-shaped towers with clouds coming out. Is that smoke? Is that pollution?
No, absolutely not. That is steam. Just water vapor? The cooling towers are part of a separate loop. Their only job is to take the very hot water that has already gone through the steam cycle and cool it down so it can be pumped back and reused. Nuclear plants do not emit smoke or CO2 during operation.
And then, looking to the future, there's the cousin of fission, fusion.
Fusion is the holy grail of energy. Fission is about splitting heavy atoms apart. Fusion is about smashing light atoms together.
Like the sun.
It is exactly what happens in the sun. Hydrogen atoms fuse together under immense pressure and heat to form helium, and in that process, a tiny amount of mass is converted into a huge amount of energy.
And why is it considered so much better than fission?
2 main reasons. First, it doesn't create the long-lived, high-level radioactive waste that fission does. The byproduct is helium, which is harmless. Second, the fuel is hydrogen, which we can get from water. It's effectively limitless clean energy.
So what's the catch?
The catch is containing a reaction that gets as hot as the core of the sun is. structurally difficult.
We're still working on the bottle to hold the star.
We are getting closer every year, but it remains one of the greatest engineering challenges humanity has ever faced.
Finally, to wrap all this together, I want to take this whole conversation to its logical extreme. We've talked about farming and energy here on Earth, but we are also running these same experiments in the harshest, most unforgiving environment possible: space.
Science off-world is the ultimate test of our understanding. If you can make these life support systems work on the International Space Station, you can make them work anywhere.
Let's talk about the Veggie Project. This is literally gardening in zero gravity.
It forces you to rethink the most basic assumptions of botany. On Earth, gravity pulls water down into the soil to the roots. In space, water just floats away in a blob.
So you can't just use a watering can.
If you just watered a plant, the water would float away and probably short out the electronics. So they had to develop these things called root pillows.
Root pillow.
They're little pouches containing a clay-based medium and fertilizer. The astronauts inject water directly into the pillow with a syringe. There are special wicks inside that guide the moisture evenly to the roots. It relies on capillary action rather than gravity.
And they've actually grown food and eaten it.
Oh yeah, they've grown red romaine lettuce. The astronauts had their first harvest in 2015. They cleaned the leaves with sanitizing wipes and ate them with a bit of balsamic vinegar.
That has to be the most historic salad ever made.
It really was. And then in 2016, a zinnia flower bloomed in space for the first time. That was a huge milestone because flowers are much more sensitive to environmental parameters than simple lettuce. If you can get a plant to flower, you can get it to produce fruit.
The note in the research about the psychological impact was really touching. It said the astronauts loved tending to the plants.
They treated them like pets. In that sterile, white, purely mechanical environment, having a living, green, growing thing provided a massive mental health boost. It reminds us that we're biological entities. We have a deep-seated need for nature, even when we're in orbit.
And the station itself, this whole outpost, is powered by the sun.
It has to be. There are no extension cords to space. The solar array wings on the ISS are enormous. Each one is 112 feet long. They generate all the power for life support, all the experiments, even propulsion. It is a completely self-contained ecosystem powered by a star.
So we've covered a tremendous amount of ground. We've gone from the bacteria making our cheese to giant cones of ice in the desert to lettuce floating in a tin can high above the earth. When you look at this whole stack, what's the big picture? What's the final takeaway?
The synthesis for me is that we are moving past the age of the hunter-gatherer, and we're even moving past the age of the farmer. We are now, for better or worse, entering the age of the planetary engineer.
We're not just living in the world anymore, we are actively hacking its code.
We are. We're looking at the fundamental laws of physics and biology, how a plant eats, how an atom splits, how water freezes. And we are deliberately rearranging those laws and processes to solve our problems. We're building closed loops where none existed. We're turning waste back into food. We're capturing the energy of the sun and storing it in a lake on a hill.
It's incredibly empowering, but it's also, it's a heavy responsibility.
It is. We are taking the controls of Spaceship Earth. We have to make sure we know how to fly it.
That leads me perfectly to my final thought for you listening at home. We're seeing all these technologies that allow us to grow food without soil, to catch water from thin air, to build our own glaciers where we need them. We are effectively, piece by piece, decoupling our survival from the random luck of local nature. So if we can do this here, are we just practicing? Is this the toolkit we're building, not just to save Earth, but to one day terraform Mars?
It certainly looks that way, doesn't it?
Something to think about while you're eating your fermented chocolate bar today. Thanks for diving deep with us.
It's always a pleasure.